Hello everyone, my name is Enes and I'm a student at the Aerospace Engineering Department of Middle East Technical University. And the presentation that I will present today is titled Size and Orientation Effects in Nanoscratch Test Studied through a Size-Dependent Crystal Plastic Framework. Is it better if I speak like this? Can you hear? Okay. So as the name suggests, it's about the nanoscratch test method, and it's a non-destructive test method similar to nano-indentation. But this time, it's not only indenting, but also scratching the material. So the outline of my presentation is as follows. First, I will introduce you to nanoscratch test methods, size effects, and the aim of the study. And I will present the theory used to model this method. And finally, I will present my results and conclude and give my outlook. So to start off, what are nanoscratch tests? This is a test method, as the name suggests, which is done through an indent scratching of the material. It's used to evaluate the tribological properties of a material, such as its hardness, wear resistance, and friction coefficient between the indented and the material. And similar to nano-indentation, it works through first an indenter geometry is used. The indenter indents through the material and scratches as shown in this figure here. And as you can see in the experiments, the scratches look like this, and there is a chip material removed due to the scratching process. Now, this test is usually done on thin films, coatings, metals, and alloys and ceramics, but I will mostly be interested in metals here. So, in this testing method, we observe something called size effects, and you might know what this is. It's describing the behavior of the material, that it gets stronger as the size of the material or characteristic size of the formation or grain sizes are decreased. So in nanoscratch testing, this phenomenon is observed frequently, similar to nano-indentation. As the penetration depth of the scratching is decreased, the material behaves harder. So here it's showing that the penetration depth is decreased as the x-axis goes to the left. The scratch hardness of the material is increased. Similarly, the grain size also has a similar effect. As the diameter of the grains are increased, as the diameter of the grains are decreased when we go to the right, we can see that the scratch hardness of the material is increased. So the material is behaving stronger at smaller scales. So the aim of this study is to capture this effect through a finite element framework. Now, conventionally, nanoscratch tests are done experimentally and they are modeled through molecular dynamics simulations. But there are some finite element studies on the subject as well, but the size effect studies are not very common through finite elements for this process because it's hard to model and the models usually don't converge and have issues. So what we have done is study this phenomenon through finite element method using a strain gradient crystal plasticity theory. And we've calibrated copper material, the material parameters of the copper through experiments. And we've examined indentation, grain size effects, and finally orientation effects, the orientation of the crystal material. So let me start with the theory. The theory follows a simple power law form, slip rate law. The slip rate evolves due to an effective slip resistance in the material, which is made out of slip resistance contribution of statistically stored dislocations and geometrically necessary dislocations. Statistically stored dislocations evolve due to plastic hardening of the material, and it follows a hypersecond law, the hardening behavior. And the geometrically necessary dislocations evolve due to the strain gradients during the deformation. The gradients of plastic slip cause the material to harden and geometrically necessary dislocations to form, and this in turn reflects the size effects in the material. So as the material deforms, plastic slip gradients occur, and this results in a density of geometrically necessary dislocations. And in combination with a length scale parameter, this is reflected into the model as an increased hardening. So the issue with this framework is that the equations are simple, but the gradient of plastic slip must be calculated. And in finite element method, since plastic slip is not a degree of freedom in this model, calculating the plastic slip requires additional finite element operations. So to start off, we have we know the plastic slip at the integration points. The IPT corresponds to integration points. And using simple finite element operations, we can extract plastic slip from nodes to the integration points using shape functions. However, we don't know the nodal values of these yet. But let's start with this equation anyway. So we have an interpolation equation, and if we take the derivative of this equation and derivate both sides with global coordinates, we get the following derivation, which can be further modified into this equation, which gives us the plastic slip gradient at the integration points based on 3 parameters. So the first of these parameters is the derivative of shape functions, and we know this from any finite element book. Additionally, we need the inverse of the element Jacobian. This needs to be calculated at each integration point during the simulation, and this is once again just calculated inside the code we've developed. And finally, what we need is plastic slip values at the nodes. Like I said, we don't know this yet. We only know plastic slip at the integration points. So the integration point values must be extrapolated to the nodes such that we can finally complete this equation and obtain plastic slip gradients. So how does this interpolation work? We modify this interpolation equation to become an extrapolation by multiplying both sides with the inverse of the shape functions. Now we can multiply inverse shape functions and plastic slip at the integration points to get plastic slip at the nodes. So here we have a small problem. Imagine a 4-element mesh, for example. And in this mesh, we have 4 elements connected at the node at the center. So if we perform an extrapolation at each of these elements, for example, an extrapolation here, here, and here, and here, we get 4 different values for the node that they are connected to, because each element is assigning a different value to this node after the extrapolation. So what we need to do is perform a simple averaging scheme at this node. As you can see, when we deattach the elements, we have 4 different values of plastic slip, because all nodes are contributing, all elements are contributing something else. So what we do here is average all these 4 values of plastic slip and finally end up with an averaged continuous value of plastic slip. Because otherwise, if we had 4 different values for a single node, we would have a discontinuous mesh. So that's the end of the theory, and the plastic slip gradients are calculated and the size-dependent behavior of the material is modeled. Now we have the finite element model of the Nanoscratch process. The model consists of 2 geometries. First of them is a Berkovich indented, which was chosen for this study. And then we have a deformable sample to be scratched. As you can see, here's the geometry of the sample. It has a very fine mesh at the scratching region and a coarse mesh at the outer surfaces to avoid boundary effects. The boundary conditions of the model are simple. All the surfaces except for the contact surface are restricted in all directions, fixed in all directions. And finally, the deformation of the model looks like this. The indenter goes into the material and scratches the surface of the material. And as you can see, now we have a deformed, scratched surface similar to the experiments. Now, from this finite element analysis, we are interested in a few outputs. First of them is the reaction forces on the indenter. Similar to nano-indentation, we want to know how much load is applied on the indenter. And not only is there a normal force in the indenter, there is also a lateral force in the scratching direction, because now we have another axis to deform the material and another force to be interested in. Scratch hardness is simply calculated as a ratio of lateral force divided by the projected contact area between the indenter and the sample. And the friction coefficient is a ratio of these 2 forces. So the friction coefficients are, from the Nanoscratch test, calculated as a ratio of forces applied on the indenter. Here, we also need to obtain path outputs to compute material pileup during the deformation. And that works through this animation you will see. So the indenter goes into the material and scratches along this direction, as I've shown before. And now we are interested in these 2 paths. The first path is along the, sorry, it's hard to see the red. The first path is along the indentation, sorry, scratching direction, the direction that indenter moves. And the second path is along the not circumference, but the lateral direction of the indenter from the sides of it. So as I said, we worked with a copper material. It's pure copper. It's an FCC material with 12 active slip systems, and the material parameters are shown in this table here. Now, we had to calibrate this copper material and our model. Sorry, not calibrate, but verify it with the literature. So we've obtained results from a study in the literature written in 2020 by Carrier and his colleagues. Here, they've computed the normal and lateral forces on the indented after deformation, and we've repeated the simulations that they've done and obtained the same results, the same magnitudes of force. So we have verified our model. We verified our model parameters and material parameters, and we have chosen to use this model in indentation size effect and grain size effect simulations. So the first example cases are about indentation size effects. We worked with a large range of normal forces on the indenter. The indenter is indented into the material through a load-controlled method. So normal force applied on the indenter is prescribed from 1 millinewton to 4096 millinewton, and the rates of loading and scratching are same in all cases. So we are working with a single crystal here. The crystal is aligned with the global coordinate system, so no weird orientations. And finally, here are the results we obtained. So we are plotting normal force versus the scratch hardness computed. How much time do I have?
2 minutes.
Oh, okay. We're computing scratch hardness and normal force plots, and as you can see here, as we increase the normal force, when we use a size-dependent model, our scratch hardness is decreasing when the normal force is increased, because the indentation size effect says that as the depth of indentation is increased, the hardness of the material decreases. And then I will skip over these results quickly. When we examine the material pileup, we can see that when we apply low magnitudes of normal load, we can see a large magnitude of difference between size-dependent and independent models here. Whereas when we use a large force, the size-dependent models don't predict a large difference, because now the model is not very size-dependent, because the deformation is large enough that we're out of the size-dependent territory. We also done grain size effect examples, but I can't show this that much right now. So what's the results of these tests are? As the grain sizes have increased, the normal forces on the indented are lower when they're normalized, which means that the grain size increase shows a reduced size effects on the material. And let me show that at small grains, we see a large amount of stress under the indenter and at the grain boundaries, and this stress magnitudes are decreased when we increase the grain size. And I can move from this. And finally, when we examine the orientation effects, we can see that at specific orientations, the scratch hardness of the material is increased, and the pile-up behavior of the material changes when we orient the crystals in these three axes by specified magnitude of degrees. At non-crystal orientation, the material piles up around the indented, whereas at a rotation around the y-axis, the material piles up in front of the indented. Sorry, I can't go over these enough. And finally, in our conclusion, we've seen that indentation size effect can be modeled using finite element methods, same as the grain size effects, and the crystal orientations show a significant effect on material pileup. And finally, by including a wear or damage model, we can also compute the chip removal or material removal during the Nanoscratch processes. Thank you for listening. That's the end of my presentation.